We have spent quite a bit of time trying to figure out how to solve first-order differential equations. Now we're going to look at why we spend all this time doing that as we answer the question, what are some applications of differential equations, specifically first-order differential equations? The first application we're going to look at is an application in growth and decay. Because quite often growth and decay is proportional to the population. In other words, what we're saying is the change in the population, I'll just call it x for now, with respect to time is equal to some constant times that population, which we're calling x. And usually we've got some initial condition that the initial population is equal to some initial value. Well, this simple differential equation is actually a separable differential equation. We can divide both sides by x and multiply both sides by dt to get an equation that we can integrate both sides of in order to solve. This gives us the natural log of x is equal to kt plus some constant I'll call c1. We can exponentiate each side, taking e to that power, and it'll leave us with x is equal to e to the kt times e to the c, which is just another constant. We're given an initial value that when time is 0, our initial population was x naught. So x naught is equal to the constant times e to the 0, which is 1, which leads us to our final solution, that x is equal to the initial population times e to the kt. Now, k is a constant of some sort that really varies based on the context that we're working in. So usually on these problems, we're going to first have to solve for that constant, and then we'll go back and actually answer the question that's being asked of us. So let's start by doing some examples. Let's say a culture, maybe it's a bacteria culture, has an initial population of P sub 0 bacteria. And at time is equal to 3 hours, it has doubled in population. The question we're going to ask is, how long will it take to triple? Well, since we've already solved this differential equation, we're going to use that brown box at the top of the screen. X is that final population. Well, first, looking at the fact that at time 3 it has doubled, doubled would be 2 times the initial population, is equal to x naught, which is the initial population, e to the k times time. Well, time is 3 hours. This gives us an equation with one unknown, k, that we can solve in order to determine the constant so that we can answer the real question. First, dividing both sides by p naught gives us 2 equals e to the k times 3. Taking the natural log of both sides, the natural log of 2 would be equal to 3k. And dividing both sides by 3, we get the natural log of 2 divided by 3 is equal to our constant. And if I plug that into my calculator, that's approximately equal to 0.231. It's a long, ugly decimal. So now we can go back to our question. We want to know how long it's going to take to triple the population. Well, if we triple the population, now the final population is 3p naught, is equal to the initial population times e to the, let's go 0.231 for our constant, times time. And we can now solve for the time in much the same way, dividing both sides by the initial population to get 3 equals e to the 0.231 times time. Taking the natural log of both sides to get natural log of 3 equals 0.231. And dividing both sides by the 0.231, time is equal to the natural log of 3 divided by the 0.231. Well, if I plug that into my calculator, we get that the amount of time it takes for the population to triple is 4.76 hours. Let's try one more example of this exponential growth or decay, proportional growth and decay. One spot where we see decay is in chemistry with this concept of half-life. Half-life is the amount of time it takes for a certain isotope to decay to about half of what it used to be. The half-life of the isotope Fe55 is 2.7 years. If an artifact has only 3% of its original Fe55 isotopes, how old is it? And again, just because it's not on the screen, I'll copy that equation we derived using the differential equation, x is equal to x naught e to the kt. First, again, we're going to have to find that k, that constant, and then we'll go back and answer the question. To do that, we'll use the fact that the half-life is 2.7 years. That means if we start with x sub 0, we'll have half as much, or half of x sub 0 left, when time is equal to 2.7 years. We can solve this quick enough, almost like our first example. Dividing by x naught, 1/2 is equal to e to the 2.7k. Taking the natural log of 1/2, we get 2.7k. Dividing, we get the natural log of 1/2 divided by 2.7 is equal to our constant. And I can do that on my calculator. The constant's equal to approximately negative 0.2567. Now we can go back and answer the original question. We want to know, we only have 3% left. How old is it? Well, if 3% is 0.03 times the initial amount, which we said was x naught, that's going to be equal to the initial amount times e to our constant, negative 0.2567, times time. And we can go back and solve it exactly the same way, dividing by the x naught. Then taking the natural log of both sides, we get the natural log of 0.03 equals negative 0.2567t. Then dividing by that negative number, we get the natural log of 0.03 divided by negative 0.2567, which means our final time, the age of this artifact, is 13.66 years. This example of an application of differential equations is pretty straightforward and simple. Let's try one that's a little more involved. Another application comes from Newton's law of cooling. Newton's law of cooling says that the change in the temperature with respect to time is proportional, or k times, the current temperature minus the temperature of the air. So where T sub m is the air temperature, or the temperature around the object. So at Thanksgiving, if a turkey is removed from the oven at 190 degrees Fahrenheit, and 2 hours later, in a 72-degree room, it cools to 140 degrees. How long until it cools to 100 degrees? Well, we have our differential equation that the change in temperature with respect to time is equal to a constant times the temperature of the turkey minus the air temperature at 72 degrees. Again, this is a separable equation. We can divide by temperature minus 72 and multiply by dt to get something we can integrate in order to solve. The natural log of temperature minus 72 is equal to kT plus some constant. Exponentiating both sides, we get t minus 72 is equal to e to the kt times e to the c1, which is just another constant. And I can add the 72 to both sides to get ce to the kt plus 72, modeling the temperature of the turkey. But we're actually given an initial value. At time 0, the turkey coming out of the oven was 190 degrees. We can use this to solve for our constant. The temperature is 190 degrees is equal to C plus 72, because e to the 0 is just 1. So our constant is equal to 118 degrees. Which gives us our final equation for the turkey is that the temperature is equal to 118 times e to the kt plus 72. Okay, now that we have an equation to model the turkey at room temperature, we're going to find the constant that describes the decay of the temperature, and then we can answer the question about how long until it cools to 100 degrees. We're told 2 hours later, we have, in that 72-degree room, it cools to 140 degrees. So it's 140 degrees after 2 hours. 140 is equal to 118 e to the k times the 2 hours plus 72. Subtract 72 from both sides to get 68 equals 118 e to the 2k. Divide both sides by the 118. It's equal to e to the 2k. Take the natural log of both sides to get out of the exponent. 68 over 118 equals 2k. And divide by 2 to get natural log of 68 over 118 divided by 2 is equal to k. Or in our case, k is equal to negative 0.2756. Now that we know our constant, our equation can even be made more specific, that the temperature is equal to 118 e to the negative 0.2756 times time plus 72. And now we're finally ready to answer the question, how long until it cools to 100 degrees? Plugging 100 in for the temperature equals 118 e to the negative 0.2756 t plus 72. And now we just have to solve in much the same way. Subtracting 72 from both sides will give us 28 equals 118 e to the negative 0.2756 t. Divide by the 118. e to the negative 0.2756t. Taking the natural log of both sides, we get the natural log of 28 over 118 equals negative 0.2756t. And finally, to get t, we divide both sides by that coefficient to get the natural log of 28 over 118 divided by negative 0.2756. And if I plug that into my calculator, I get 5.22 hours. And that's Newton's law of cooling. Turns into a differential equation, which we know how to solve by using separation of variables. What's interesting about Newton's law of cooling is the air temperature could be a function of time. The air temperature could be changing as well, which would change this to a linear equation instead of a separable equation, but it would still solve in much the same way, just changing the separation of variables into the linear equation that we know how to solve. Speaking of linear equations, I want to do another type of example that turns into a linear equation, and that are what are called series circuits. A little bit of setup about series circuits. We're going to talk about two different types of series circuits. We've got an LR circuit. The idea behind an LR circuit is we've got some energy source, usually like a battery, that's connected to this spiral thing called L, the inductor. And then it comes around and connects to this jagged thing, which I'm going to call R, the resistor. And if we say I is the current flowing through this system, it turns out we can get the differential equation L times I prime plus R times I describes or is equal to the amount of energy coming out of that energy source, whether that's a battery or some other type of energy source. Really similar to an LR circuit, it's what's called an RC circuit. An RC circuit has the similar energy in the battery, and it's only going to go through R, which we already know is the resistor. And this time, it's going to go through this thing that's called C, the capacitor. And then we can describe with a differential equation Q, which is the charge in this system. Turns out we get the differential equation, the resistor times Q prime, plus 1 over the capacitor times Q is equal to the energy in the battery, or whatever we're using to get energy out of, where Q is the charge that's coming out of this circuit. And I want to notice in the first differential equation, we were talking about current. The second differential equation, we were talking about charge. And it turns out that the two are closely related. Current, I, is the change or derivative of the charge, Q. In other words, Q prime is equal to I. Q, the change in the charge with respect to time, is equal to the current that's moving through the system. So these two equations are closely related, and when we do higher order differential equations, we're going to bring them together into one. But for now, let's do one example using current. Let's say a 12-volt battery is connected to the RC circuit with resistance that's from the resistor, of 100 ohms, and capacitance of 10 to the negative 1 farad. Find the charge and current if Q sub 0 is equal to 0. In other words, the initial charge is 0 when this thing gets turned on. Well, we know we've got the differential equation up above that RQ prime plus 1 over CQ is equal to E. In this case, R, the resistance, is 100, Q prime, plus the reciprocal of C. The capacitance is 10 to the negative 1. The reciprocal is going to be just 10. Q is equal to the energy. It's a 12-volt battery, so we're going to get 12 volts out of the system. Well, this gives us a linear differential equation, and we know how to solve linear equations. We'll integrate the middle function, 10 dt, which just gives us 10t. And we know if we multiply e to the 10t on both sides, it'll give us a real nice product on the left of e to the 10t times the q prime is equal to 12 e to the 10t. And we can take the antiderivative of both sides to get e to the 10t q is equal to 12 divided by 10 is 1.2 e to the 10t plus a constant. Dividing both sides by e to the 10t, we get q is equal to 1.2 plus e to the negative 10t times our constant. We're given an initial condition of 0, 0. So if I plug that in, 0 is equal to 1.2 plus e to the 0 times the constant. And so we know our constant is equal to negative 1.2. Putting it all together, then, we now can get the function for our charge Q. Q is our charge. Q is equal to 1.2 plus our constant, which is negative 1.2, e to the negative 10t. That's our function for the charge over time. But we were also asked to find the current. Current is the derivative of the charge. I, the current, is equal to Q prime. So we'll take the derivative of Q, which is 0, plus 12 e to the negative 10t, taking the derivative of the Q to get our final function. We've taken a look at several applications of first-order differential equations in this video. Now it's your turn to practice these. Good luck as you do so.